Okay, so let's talk about a couple of things before we get started. I have decided that we're going to drop the lecture that I had planned on herbivores and defenses, and we will stick to the schedule of next Monday being the exam. So we'll have one fewer lectures on the next exam. We'll talk about parasites today. We'll spend Wednesday and Friday talking about mutualism, and then the exam will still be on Monday. I think that if we try to move the exam, it's going to cause problems it's going to cause multiple problems. So I'd rather really not do that. I think we just sacrifice a lecture. Okay. Also, I had thought that I was going to try to get in contact with all the groups who are going to try to work on a project and talk it over and find out where you are. And that didn't happen last week, so it's going to happen this week instead. And we'll see who's still in and if anybody's out, whether we need to make some arrangements. The homework is up to date. So you had 3 assignments that I hadn't gotten back to you. They are all here. Put your homework that you're turning in here. And the keys will be up later today, along with, I'm hoping, now all the study guides, now that I know what's going to be on that 3rd exam. So today we're going to talk about a special case of exploitation systems. There are really two special cases that I like to talk about. One of them is herbivory, because that's what I do, that's my research, but we're skipping that this semester. Because for most of you, it's more interesting to talk about disease as a special case of exploitation. And there are some really interesting things about diseases and parasites as exploiters that affect the practice of medicine in humans. So it's, I think, worth talking about those things. Now, really fundamentally, when we talk about diseases or parasites like tapeworms, we're talking about exploiters that steal resources from a host. So they're not a predator killing and consuming a prey. They're not a parasitoid which utilizes the internal parts of a host and then has to kill it to complete its life cycle. We're simply talking about organisms that use the resources of another organism to make copies of themselves. The fact that they may cause the death of that host is a complete accident, and it's not necessarily a good thing. Because if you are living within a host and you cause its death, well, you die too. So this raises some special concerns about exploiters that have the habit of being parasites. So today's focus then is on organisms that steal resources from other organisms to make copies of themselves. If they happen to cause the death of the host, that's complete accident. So we can still consider how these organisms would work as a standard exploiter-victim system. And we can use those predator-prey graphs that we got, that you just did some homework on, and examine those. And so what you'd see is that the way that we phrase increased efficiency of a parasite is virulence. Virulence is the ability to cause illness or death. Why do we focus on virulence if we're talking about resources? Because the more resources a parasite steals, the more likely it is to cause illness. That is, the host cannot use those resources to maintain itself. It becomes ill. Eventually it becomes dead. So virulence is the specific term that we use when we're talking about the efficiency of a parasite. Now, a parasite's efficiency is simply the rate at which it can convert resources into copies of itself. So if a parasite is able to steal resources rapidly and at a large scale and convert it into lots of copies really rapidly, it's highly virulent. It's very likely to cause illness and sometimes death. If a parasite is sluggish, sort of sits in your internal system, kind of trying to evade your defenses, and gradually stealing resources, and over time making copies of itself, then it's relatively less virulent. Okay? Now, we had an analogy here between virulence and efficiency of a predator. What's the analogy between the reciprocal selection on the prey and the selection on the host? So if a parasite's stealing resources from the host, what does that select for in the host? Ideas? Shindy. What does it select for in the host? You gonna just let a parasite steal your resources? Really?
Maybe the one with the strongest immune system.
The immune system. Okay. Host resistance. We don't think of it as rabbits running away from coyotes, but it works the same way. It's resistance. It's the immune system. The innate immune system. The cell-mediated immunity, right? Which recognizes and kills those parasites. So selection on the parasite for increased virulence will cause illness and death in vulnerable individuals, and they won't reproduce well. But the ones that have high levels of immunity, resistance, they will be the ones that are left over, and they will do the reproduction. And so the population of hosts over time will become more resistant. Oops, and there we see that, host resistance pushing back. Now, if you're really virulent, where's the equilibrium? Sarah, stable or unstable? A really virulent parasite will do what to its hosts? Well, which side of the hump is it on? Okay, which side of the hump is it on? Okay, and what does that mean? Unstable, which means the hosts will do what? They'll be liable to, Nini? What? Nothing? What? Death. Okay, yeah, they'll go extinct. A really virulent parasite will kill its hosts. The parasite will cause the extinction of the host. Okay. The fact that you evolve resistance tends to stabilize this interaction. Okay. So the way that we think of this is then that the parasite is continually experiencing selection for high virulence, and the host is continually experiencing selection for immunity. And the balance of that interaction is determined by the rates of selection. If the host is selected for immunity at a higher rate than the parasite is selected for virulence, then the host will eventually become immune. Because we will push this interaction all the way here, first to a stable interaction, where the parasite's still able to steal resources. But if we're selecting more strongly on the host than the parasite, where do we go here? Look at that. There's no density of hosts that can support the growth of the parasite. That means that the host has permanent immunity. And the disease, the parasite, goes extinct. So this is what vaccination aims to do. It aims to push this isoquine way over here so that the parasite goes extinct. So do we see this in action? Do we see reciprocal selection? Actually, host parasite systems are one of the best places to look for that coevolutionary arms race that we talked about. The Red Queen, where you're running in place as fast as possible just to stay in the same position. So you're selecting on the parasite for higher virulence, you're selecting on the host for higher resistance. And if one of them outdoes the other, then the other partner will go extinct. But if they match, there'll be a relatively stable interaction somewhere in there. So do we see waves of selection on parasites followed by reciprocal selection on hosts? The answer is yes. Here we go. Okay, this is a illustration of the Red Queen in action. And as I said, parasite host systems are some of the best systems in nature to see this. So here we have a disease and host system. This is wheat rust growing on wheat strains. And here's 1956 through 69. And here is the frequency of different strains of wheat rust. So strain 10 started out at maybe 15% of all infections in the wheat population in North America. Okay? And what happened over time? Well, by 1960, what had happened to this strain of rust? It went extinct. And what had taken its place? Strain 17. Okay, and now why would strain 10 have gone extinct? It's a disease, perfectly good disease. What happened to cause the extinction of strain 10? It didn't kill all the wheat. No, because you've got other infections in wheat up here. No, didn't kill all the wheat. What's that, Keach? The host population had gained immunity to this strain. So it could no longer infect the population. It went extinct. These are genetically different strains, strain 11, 9, 15, and 17. And strain 17 increased in the population. Why was strain 17 able to increase at the same time that strain 10 went extinct? Nathan, what's up? Strain 17. Why is strain 17 increasing while strain 10 is going extinct? Because it's new. And because it's new, what's true? There's no immunity yet. There's no selection on the host for immunity. They have to be exposed to this strain before they gain immunity to it. So it was able to increase, killing off some of the most vulnerable wheat and leaving some of the most resistant wheat left in the population. And over time, the resistant wheat came to dominate the population, and strain 17 did what? Madison, what did strain 17 do right here? It went extinct. Because over time, over this 13-year period, strain 17 got into the population, which was not immune. It was vulnerable. And strain 17 killed a bunch of wheat. But in doing so, it exerted selection for resistance. And so in this period of time here between, or right around 1960, there was very strong selection in wheat for resistance to strain 17. Only the most resistant plants were able to survive, and that led to the eventual extinction of strain 17. So look, each of these strains is genetically different. And what you're seeing is repeated selection episodes. First on the parasite. Parasite is selected for greater virulence. It increases. And then, because it's selecting very strongly on the host, you have selection for host immunity. And eventually that strain goes extinct. Now, notice that rust as a disease does not go extinct. And that's because we are selecting for different genetic variants. We are in a coevolutionary arms race. As soon as the population gets resistant to 10 or to 11 or to 9 or to 17, another strain takes over because there's strong selection on the parasite. As soon as a new strain invades, like strain 17 here, selection on the host starts to work towards its extinction. Okay, and here's strain 18 came in and it was dominant in 1969. We don't have what happened to it, but eventually that strain would also be driven extinct by host immunity. Okay, now, there's something else about diseases that is working in a kind of counterintuitive way. We expect selection on a parasite to follow the same general pattern as selection on a predator, right? So selection makes predators more what? Jasmine.
Selection makes predators
More what? Yeah. What does selection do to predators? They're in competition with each other for resources. So what does selection do? Who wins? The most what?
Oh, the most.
The most, well, what defines a fit?
Strongest.
Most furriness, basically.
The ones that are most efficient at getting food, getting resources, right? Okay, so let me tell you a story. Let me tell you a story about everybody's favorite disease, syphilis. The origins of syphilis are controversial. People blamed Native Americans for years and years and years and years. And the story appears to be more complicated than that. Syphilis is a member of a complex of diseases including yaws, pinta, and endemic syphilis, and they're common throughout warm regions of both the Old World and the New World. Yaws is an African disease. Okay. Pinta, I believe, has been found throughout the Middle East from, as long as we've been seeing skeletons with evidence of infections. So what it looks like is that Columbus did in fact bring back a form of something in that family which was able to mutate in European populations and cause the disease we know today. Now, syphilis is a sexually transmitted disease, but does anybody have a clue when the first recorded cases of syphilis appeared in Europe? Didn't appear in the Middle East, but the syphilis that we know today appeared at a specific time in a specific place in Europe? Anybody have a clue? Okay, the invasion of Naples by the French army in 1494, very specifically. Okay, and they called it the French disease because it was the French soldiers who were suffering from the outbreak. Now, what do you know about syphilis? Is it a deadly disease? It is a chronic disease? Who knows something about it? Anybody? Taylor?
Spreads to your brain.
What's that?
Spreads to your brain.
What does spread to your brain? So,
Untreated, it spreads to the brain.
right. Okay. So you can get neurosyphilis, right? How long does that take to develop? Years. Okay. Well, at the invasion of Naples, it was killing French soldiers within a couple of weeks of contracting it, and it was about 95% lethal within 2 weeks. Does that sound like syphilis? That you know? No. So what happened? What happened? Is it the evolution of immunity? Well, gee, I would suggest that probably all the people in the early 20th century who were confined in asylums because they had syphilis would argue that no, it probably wasn't because we had evolved a lot of immunity. Something else was going on. Something that is unique to parasites that you don't find in parasitoids or predators. It's, what's that?
Became less virulent. Became less virulent.
It did. It evolved lower virulence over time. Even though the host did not evolve higher immunity. The parasite itself evolved lower virulence. Does that make any sense?
Yeah. They're keeping the host alive.
They're keeping the host alive. Why is it important to keep the host alive? What is so different about parasites than predators and parasitoids? They don't care.
Parasites need the host to live.
Parasites need the host to live. If a parasite kills its host, the parasite dies. The parasite can deal with that if something in particular happens before the host dies. What has to happen before the host dies for this to work?
It's a bland spread.
Multiply is virulence. What's the other thing you said?
Spread.
Spread. Spread where? To another host. It must be transmitted. Neither parasitoids nor predators have a transmission barrier. Parasites have a transmission barrier. And that is why they behave in unexpected ways. Parasites must be transmitted. A parasite that kills its host before being transmitted to another host is a really bad parasite. Now, this is really interesting because what it says is that there are two forms of selection on parasites. There's your standard selection for virulence. And virulence is efficiency, right? And why do you need to be efficient? Because you are in what with other parasites? Competition. The most virulent parasite makes the most copies of itself inside the host. But is that the best parasite? Maybe, maybe not. It depends on the rate of transmission. A parasite that is transmitted rapidly can sustain a high level of virulence. Because you can make a bunch of copies of yourself, you can make your host very sick. If you can get transmitted, it doesn't matter. But if it's difficult to transmit, you cannot sustain high virulence. Parasites will inevitably be selected for lower virulence because they have to keep the host alive long enough for transmission to occur. This is unlike parasitoids and predators. So the transmission barrier is pretty unique to parasites. And we tend to then use different models because we recognize that things are going to follow a different course of action. Over evolutionary time, we're going to see parasites change from really virulent things that for which the host has no immunity when it's newly introduced into a population into chronic infections. In fact, every one of the communicable diseases that we suffer from today started out that way. They were lethal. They were killers. Where did they come from? Measles came from domestic animals, like cattle. Measles is related to the rinderpest virus. When we first started herding animals, we got that disease. And it burned through human populations like that. Okay, now measles is still a very serious disease. If you know anybody who's not vaccinating their kids because of all the bullshit on the internet, tell them that they're killers. Tell them that there is a movement already afoot to hold them criminally liable for infections to other children. Now that we can do the genetic signature of a specific infection, we can trace a specific infection to an unvaccinated kid, and we can hold that parent criminally liable. And that's going to happen. You're going to see that happen. If you don't get the parents to vaccinate with a carrot, get them to vaccinate with a sentence of 10 to 20. That's going to happen. Okay. All of our diseases are like this. All of them were not really sustainable in primitive populations that had very low densities because they're rapidly burned through the susceptible individuals and they couldn't be transmitted, so they died out. It was only when we settled down and started doing civilization that we got the diseases that we have today. The only exceptions are insect vector diseases like yellow fever and malaria. Those have been with us forever. Okay. But now, we know that over evolutionary time we see this trend towards lower virulence, but we also now know that we can see selection in action on parasites and reciprocal selection on hosts in evolutionary time. So we can see a parasite expand in a population, burn through it, and then the population start to get immune and cause the extinction of that infection. So we use a different type of model to illustrate the courses of these parasitic infections, and it's the SIR model. Okay, and it's not terribly hard to do. We're not going to actually do a lot of calculations with this, but I want you to understand the basic structure of the model. So S is the number of individuals that are susceptible. Okay, I is the number that are infected, and R is the ones that have developed resistance. So I think you can see we could apply something like this to your average flu outbreak every fall. Get your flu shots. It's already started. There's also something that we need to know about the rate of transmission, okay, and then the rate of recovery and development of immunity. So this is not a really complex model, but basically the probability of contact between susceptible and infected individuals is just the number of susceptible times the number of infected, more or less, or the proportion susceptible times the proportion infected, which is probably the more useful way to do it. Okay? And the rate of infection is the rate of contact times the transmission rate. And that's equivalent to the birth rate of the infection. So we can model the infection as if it were a population. We have a birth rate, and then we have a death rate, which is the number of infected individuals, or the proportion, times the rate at which individuals recover. So just as we use births minus deaths to model things like your standard Lotka-Volterra predator systems, you can see that D parasite dt equals S times I times G minus I times V. That's all it is. And the ratio of this to this tells you whether more infections are starting, in which case this would be greater than 1, than dying. So if this is larger than this, then more infections are happening than people are recovering. That means the disease is spreading. If this is less than this, then it's like a number less than 1, and the infections are declining. So we use that ratio, which is really handy. And it's basically R0. This is the number of infections, equivalent to the number of infections that a single infected person will generate during the course of their disease. And if this is greater than 1, the infection will spread. If it's less than 1, then it dies out. So we can look at how this ratio changes during an infection. Okay, first thing to understand is that early in the infection, there are not going to be a lot of these guys, but there are going to be a ton of these guys, right? There can be a lot of these guys. So this is going to be a large number. There won't be a lot of these guys, and so a small number times the rate of recovery, this is going to be less than this. Early in an infection, you have a lot of susceptible individuals and not many individuals recovering. So by definition, this is going to start out and increase rapidly. And at some point, you'll reach an inflection point. This will equal this, and then the number of infected individuals will be so high that this quantity will be less than 1, and the infection will start to die out. So we can graph that. So here's the susceptible individuals, right? And that starts out basically at 100%. So our infection rate is going to skyrocket early on in an infection. But then the infected individuals are going to peak and then start to decline as individuals start to recover or die, one or the other. They're not available anymore. So right here, you can think of R0 as being greater than 1, the infection is spreading. Here, R0 is less than 1, the infection is starting to die out. This is the actual base model that epidemiologists use down at the Tulane School of Public Health when they're tracking things like this. They use more sophisticated versions of it, but this is what it is. It's simply this model, SIR. So what I want you to understand about this is what the significance of this ratio is and why it starts out being greater than 1. It starts out being greater than 1 because everybody's susceptible and nobody's infected yet, or very few individuals are infected yet. So there are a lot of individuals that are getting infected and very few have recovered yet. That means the infection, by definition, starts to increase early on. And at some point, when you get a lot of infected individuals, they start recovering at a rate where they're immune, and this has to peak and then start to decline. And that's what this graph is representing here. Okay. So this is exactly the way that an epidemiologist would deal with the rapid selection on parasite and host. The selection on the parasite precedes the infection because you have a new parasite for which the host has no immunity. So that's already been selected for. And what we're tracking here is the rate at which the infection is causing, in ecological time, the evolution of resistance. Okay, this is not something that we see in either parasitoids or predators because we're talking exclusively about evolutionary time in those interactions. Over evolutionary time, coyotes get faster and then rabbits get faster in return. But this is in ecological time. This is the internal dynamics of the immune system causing this cycling. Now, the interesting thing is that most diseases do cycle exactly like this. And you'll see a particular strain of a disease reach peak and then decline, followed by, after a lag period where selection has gone on in the parasite, another infection cycle, followed by a peak and a decline. This is exactly what goes on with influenza. Okay, so it's important to understand the transmission barrier for parasites. It's important to understand the rationale behind this little model. We have a lot of infections increasing here because there are a lot of susceptible individuals. The infections are declining here because you got most of the infected individuals, most of the populations has been infected or is infected, and there are not many susceptible individuals left to infect. So it's going to crash. Okay. The other thing about parasites is that transmission barrier is crucial. It's crucial to understanding that disease is an ecological interaction that we can apply in our own lives. Disease is not primarily a medical thing. Disease is primarily an ecological interaction. And you can medicalize it all you want. You can get all the drugs you want, but all you're doing is selecting on the parasites. If you mess with things like the transmission rate, that will have a greater effect on the course of disease in human populations than any number of antibiotics. And you know what? Much cheaper. Let's use the example of HIV. Okay? So HIV is a zoonotic disease, as really all of our transmissible diseases are. It existed in great apes in Africa for Lord knows how long, and got into people repeatedly, probably as long as there have been people in Africa. So why are we just dealing with it now? Because HIV was isolated in small communities that did not have a lot of contact with each other. What's changed? The opportunities for transmission. Modern development has connected formerly isolated communities, allowing HIV to spread. That's why we're dealing with it now. HIV also illustrates the same phenomenon as syphilis does. It started out as an acutely fatal illness that killed within a few months. And now, at least in the Western world, it is a chronic manageable disease. That's not the case everywhere in the world. In Southeast Asia, in parts of the Middle East, and in sub-Saharan Africa, it is still a highly lethal disease. Okay, and there's really good reasons for that. One of the main reasons for that is simply the availability of drugs, but there are other reasons. There are lots of areas of the world where drugs are not widely available and HIV is a chronic disease. It is of low virulence. What does that tell you about the transmission rates? In areas where the virulence of HIV is low, what can you say about the transmission rate? Transmission rate is also low. In areas where HIV still remains virulent, what can you say about the transmission rate? It's very high. It's the availability of things like condoms. Contrast the availability of condoms and the cost of making condoms with the availability of HIV drugs and the cost of making and distributing HIV drugs, which is more cost effective. You can affect the transmission rates of diseases in your own lives, and you can force them to become less lethal. It is extremely important, whether you engage in those behaviors or not, that you understand that you affect the lethality of the diseases that afflict you. So that transmission barrier is under our control in many cases. Also explains why things like Ebola are never going to be a big problem. Ebola is a really rapidly fatal and highly lethal disease. But what can you say about the transmission of Ebola? What is required for that? Direct contact with infected body fluids. So if a healthcare worker who's treating a case of Ebola simply puts on gloves, it will break the chain of transmission. Ebola is too lethal. It is not a good human disease, and it will never be a threat to humanity as a whole unless the transmission barrier goes down. So be careful about that transmission barrier. Let's finish up with one last thing. Since there are transmission barriers, this selects for particular things about parasites. And many parasites have complex life cycles to help them get over that transmission barrier. Think about a parasite in an organism that lives during the summer, right? And it overwinters in some stage, but there are no hosts during the winter. Well, oh dear, what happens to the parasite? When all the hosts die that year, the parasite's going to die. It's going to go extinct, unless it can find a different host that will carry it over the winter. This is the classic primary and secondary host syndrome. So the primary or definitive host in a parasite we define as the host in which sexual reproduction occurs. Usually what you see is that a parasite will have sexual reproduction in one host, it'll flood out of that host trying to desperately to find a secondary host, but it won't reproduce sexually in that second host, it'll just reproduce clonally. And then when it gets the chance, those clonal organisms will burst out of the secondary host and try to infect a primary host in which they can sexually reproduce. So the secondary host is one in which some stage of development occurs, usually asexual reproduction. So you may get a single parasite infecting a secondary host, but it will multiply to produce many copies of itself to ensure that it gets back to a primary host eventually. There's also, in rare cases, something called a transport host, which is just you get infected and nothing happens, but that transport host serves to get you from one primary host to another primary host, or from a primary to a secondary host. So you can have 3 or 4 or 5 different hosts for these parasites. And you can have them alternating in generations. So the classic example that everybody finds easy to understand for us is malaria. So let's finish by looking at the malaria life cycle. So malaria for us begins when we get bitten by a mosquito. So the mosquito injects malarial sporozoites into blood, right? Okay, now you've got a case of malaria. Well, the little sporozoites then infect red blood cells. They first go to the liver. I'm not going to go through this whole thing in great detail, but they change form into merozoites, and that is one reason why malaria is difficult to treat. Different surface proteins on these cells than on these cells. Okay, but eventually they infect the red blood cells. They cause the symptoms of malaria: chills and fever. And that's related to waves of infecting red blood cells and bursting them apart, releasing their contents, which cause inflammation. That causes the fever. Okay. So these merozoites are circulating in human blood, and then they develop into sexual forms, either male or female gametocytes. And for those of you who have bad dreams about the plant life cycles from 1073, 1071, this is the same kind of thing. More bad dreams. But this is what the mosquito ingests. And as the mosquito ingests these from you, they undergo sexual reproduction to form new sporozoites that infect the salivary glands that get injected into the next human. So where's the sexual reproduction? Which host has sexual reproduction of malaria? The mosquito. The mosquito is the primary host of malaria because that's where sexual reproduction of the malaria parasite occurs. People are simply malaria's way of finding mosquitoes. Malaria doesn't care about us. Malaria wants to be in mosquitoes because that's where sexual reproduction occurs. But if you're adapted to living in a mosquito, how do you get from one mosquito to another? You can't. You need a secondary host. That's us. Or it could be one of the related species that carry related strains of malaria, like primates or birds. Bird malaria is thought to be one of the precursors of the 4 strains of modern human malaria. So these are diseases that jumped once again from other animals into humans, but they did it millions of years ago because, as far as we can tell, we have always suffered from malaria. But the ironic thing is that malaria doesn't care about us. It's just using us to get from one mosquito to the next. We are secondary hosts, and I hope that humbles you, because malaria has killed more people over human history than anything else. Probably all other things combined. And it's not a complete accident, but it's a complete byproduct of malaria trying to get from one mosquito to another. We are the secondary host because this is all asexual reproduction. Okay, we will talk about mutualism over the next couple of lectures, and we'll get all the study guides up, and we'll review for the exam on Monday. Oops. Please get your homework if you've got it, and leave your homework here.
Do you have a stapler or just
Just fold it and I'll staple.